Hello, everyone. I am excited to welcome you to today's webinar. So today we are having two presenters from Epsilon Data Science, and I'm very glad to welcome them. So the first presenter is Dr. Jędrzej. Jędrzej is a senior data scientist at Epsilon Data Science, and we'll also have Damian talking to us. So we have two interesting topics to listen from today. So the first one will be preserving wildlife service with computer vision, and the second one will be scaling Shiny apps dashboard on a budget. So Dr. AJ has a background in theoretical and mathematical physics, and is currently focusing in exploring of computer vision and application of the tools that are involved. So one thing Dr. AJ wants us to know about himself is that he enjoys skiing and ice skating in his free time. So welcome. And on the other hand, Damian has a bachelor's degree in electronics and communication, and has interest in cloud services and DevOps methodology and cybersecurity. So these are very, I think, interesting topics to be covered today, and I hope everyone will enjoy. So, and I'm also being supported in the co-hosting with by Marcin. So, Marcin, please, you want to say something?
Oh yeah, thank you, Christopher, for that kind introduction. We are really happy to have the cooperation across Europe and Africa. So it's really kind of you that you can host those meetings with us. So today we will have two speeches by Appsilon Data Science. They are the sponsor of this event. They are supporting YR community and Warsaw R meetups from some time. And today they are presenting as well. Besides their talks, they will also have hiring positions that will be available at their company. If you are interested in joining Epsilon, there are job descriptions linked in the description of the video. And I hope that also Jędrzej and Damian will have some more details about recruiting. But yeah, feel free to ask any questions on the chat and have a look at the job description as well. And please enjoy the webinar, and Jędrzej, good luck with your talk.
Thank you. So let me start by sharing my screen so that you can see some slides that I've prepared for today. So Marcin, maybe let me know when you'll see it. Great. Whoop. Right, so indeed, thank you for the kind introduction. I'm Jędrzej Świeżewski. I work at Appsilon, and today I'll be telling you a bit about our efforts to help preservation of wildlife with computer vision. So I should click here. The plan of the talk is the following. I will start by describing one of the efforts which go under the umbrella of the AI for Good initiative at Appsilon. And it will be concerned with, as I said, the conservation of wildlife in Central Africa. One of the main contributions from our side was the development of a computer vision system, which I will tell you a bit about in the second point. But I will also try to argue how this particular system made an impact in the conservation efforts. And lastly, I will describe how this whole thing is relevant, or is especially relevant to the R community. So let's jump right into it. At Epsilon, we are experts in building decision support systems, as we like to call them, or in other words, interactive data visualization tools, which allow different parties to interact with their data and to draw insights from them. But apart from that, we also have a team who is very skilled in machine learning and in particular in computer vision. And although in our day-to-day work, we support commercial customers in their efforts to get insights from their data and then act upon them, we also have an initiative called AI for Good, which basically supports our efforts in contributing to the world at large in ways that we find good for the world. So I would like to tell you a story about one of such efforts. And in this work, we have collaborated with experts from University of Stirling and also the National Parks Agency in Gabon. So as you may know, Gabon is a country in Central Africa. And as you can see already from the satellite image, it's covered mostly with, or there's a lot of equatorial forests in this country. And in those forests, there are multiple national parks that host pristine ecosystems, which are very precious to the world at large, because they are home to many large African mammals, which basically need to be need those places to in order to thrive. And when we're thinking about the climate crisis currently taking place on Earth, we tend to think that those ecosystems which are separated and denoted as national parks are somehow safe from the effects of the crisis. But that turns out to not to be the case. And in fact, many of those animals living there are deeply impacted by the crisis. And in order to understand, quantify how big that impact is, and possibly act upon it, so in order for the policymakers to be cautious of what is going on in those ecosystems, we need to monitor them somehow. And the way to do that, or one of the one of the ways which is recently growing in popularity of monitoring those ecosystems, uses or makes use of camera traps. So let me describe how the typical workflow in such a case looks like. So basically what happens is that you plant, or wildlife conservationists plant camera traps, which are small devices, examples of which you can see on the left-hand side. Then you put them in various places in a forest, for example, in Gabon. And those small devices basically consist of a camera and a sensor, which is typically a motion or a heat sensor, or both. And then whenever an animal crosses in front of such a device, the device takes a photo, and this photo can then be analyzed. Now, the thing is that in order to, because those ecosystems are located in some remote areas, we cannot just simply upload those images because there's basically too poor reception there. And therefore, what typically happens is that the conservationists place those cameras, and then once every now and then, they go to collect those images. They collect them typically in batches of tens of thousands, and then they need to make use of this data. So basically, they are spending typically a few weeks, think of it as 4 or 5 weeks, just going through tens of thousands of images and sorting them into, for example, different categories. So identifying the species that can be seen in the individual photos, or also filtering out images which supposedly contain no animals at all. Once those images are classified into the shown groups, what can happen next is that they can run some ecological modeling on top of that to draw ecological insights from about those ecosystems. You can think of it as some metrics like species richness, or maybe you can monitor activity of certain species. And then you can use that as proxies for the entire ecosystems. And once you have this analysis, you can go to, you can either draw scientific conclusions about those ecosystems, or you can advise the policymakers in making the right decisions, or at least seeing the impact of their past decisions on particular parts of those ecosystems. Now, what we have done, or what the experts that we've worked with have asked us to do, was to improve this workflow, or assist them in their work by limiting the amount of time which needs to be spent in the initial phase. So basically, we have developed a computer vision system which instead of requiring the conservationists to spend several weeks on classifying the data, can do that job for them in a day. And this is important because if they save so much time on classifying the data, then they can spend much more resources on doing the ecological analysis, and therefore they can understand the systems better and inform the policymakers in a more knowledgeable way. So let me tell you a bit more about how this system is devised, or what our effort consisted of. So basically, we were approached by the conservationists with a data set that was a data set of images from the camera traps. But this was a huge data set of 1.5, actually over 1.5 million images, which came from multiple national parks, being collected in multiple studies. They came from different camera types. They were of very varying quality, and actually different settings were, the cameras were having different settings when the images were taken. So this was a huge and diverse data set. We've singled out 27 animal species that we focused on. And then once we've dealt with the richness of this data and the messiness of this data, we were able to actually build this computer vision system. And the backbone of the system is, of course, a computer vision model, which was based on neural networks trained in FastAI, which is a wrapper, Pythonic wrapper library built on top of PyTorch. And we have trained those models in the cloud. We have used cloud resources provided to us by Google on a research grant, which was dedicated to that research. So typically, when you talk to someone who works in machine learning or in computer vision in particular, they will tell you that that 80% of their time is actually dealing with the messiness of the data, and only the 20% that is left is the real fun part, where you can do some fancy modeling, and that's the part which many people say they enjoy much more. So what I would like to argue is that one of the benefits of working in the AI for good sphere is that you get to enjoy the 80% as well. And I want to provide an argument by just showing you the images. So these are images, actual images from the data set that we received from the experts. And I would like to point you, for example, to the image in the top left corner, where you can see a photo of a rare golden cat, which is the least known or the least studied large African wildcat. So such images are pure gold. Now, those images, of course, were selected from the vast amount of images to show how nice they can be. But many of those images are way more challenging than those. And here's another example. This is an example of an image that was actually classified by the experts as empty. And with this image, I want to give you a sense of the amount of work that those experts have to put in to actually draw the conclusions from those data sets or from such data sets. Notice that I've mentioned before that they have to go through tens of thousands of images like that and quickly identify what type of animals is visible in this picture. So it's really it requires a very high level of concentration, but also focus, but also a lot of knowledge about those particular species. And back to this example in particular, this image was actually classified by the experts as empty. But we realized when working with the data that our models sometimes tell us that there are animals in images that are classified as empty. So of course, the first thought is, well, the models are wrong. But then we realized that there are some cases in which they are very certain that there is an animal. And our model was very certain that in this image, there is a bird. And actually, it was a Nkulengu bird that the model was seeing in this image. So the question to you is, do you see the bird? Well, it took me some time to find it, but I did. So if you look at this area highlighted with the blue color, you will see that there is indeed a bird with its black beak turned towards the left, its body behind the branches, and then there is even the characteristic red leg of the Nkulengu rail, which goes from one of the leaves to the other one. So with this in mind, you can now appreciate how hard a task it is for the conservationists and for the models. So that's all well. We can say, okay, we've built a model that sometimes surpasses even the abilities of the experts. So that's all great. We have preserved wildlife with computer vision. Well, not so fast, right? We just build a model, but in order to actually have any impact, we need to make use of this model. And in this part, I would like to tell you a bit more about how we have used the model to actually help make a difference. And there are a few applications I want to discuss. So firstly, the main goal of the initial part of the work was to build a model that can be used by those conservationists on the ground. So those people who actually go into the forests, they actually collect the data, and then they sit with their laptops with very poor internet connection, and they need to go through those images. So a typical scenario of usage of a computer vision system these days is that this computer vision system or model is hosted in the cloud. You upload your images to the cloud, the model runs there and provides you the results. Now, this is not going to work in remote areas of Central Africa because of the connection bandwidth. So what we have done is we've built an app that is open source, and you can find its code on our GitHub account in this repository. And here is a screenshot or a capture from an interaction with this app, in which you can actually upload your images, and on your laptop without internet connection and without a need for a GPU, you can classify the images and then draw some first conclusions from that data set. So look at the time presence of certain species, look at the geographical locations of the places where those animals were spotted. And with that, you can proceed to the ecological modeling. Now, we have built this app for the national parks in Gabon. However, it is already it is now being tested on the ground there, but it is also being developed further to be adjusted to the needs of 4, I believe, more Central African countries. Now, a second application of that model that we've developed is a paper that we have built, that we have co-authored, and which is available on bArchive under that link that you see at the bottom of my slide. In this paper, what we do is we compare the ecological insights coming from those ecological analysis when they're based upon the classification done by the experts versus the classification done by our models. And the conclusion, spoiler alert, is that there is no statistically significant difference. So in fact, we can speed up the process from typically a couple of weeks to a day and still get the same quality of results. And lastly, I want to mention some ongoing study of the yaws disease, which is a skin disease which happens to spread in the gorilla community in Gabon, and then our model is being used to speed up the analysis of the data collected in order to monitor the spread of this disease. There are actually more applications, but they are at then stage too early to be mentioned on this slide. So with that, I would like to now answer the question, what if I'm an R user? So you might have spotted that the model that I've built or that I've described, those models were trained in FastAI, which is a Python library. In fact, this application that we've built is also based on Python or has Python running underneath. So what can you do if you are an R enthusiast, or maybe your organization uses R, and you're bound to that language for that reason. So the good news is that there are a few ways you can still make use of FastAI or of other models, even when they are trained in Python. So let me describe those three approaches that I would advocate, and you can find the details of how to actually make use of them. So some small examples worked out in that repo that you see a link of at the bottom of the slide. So firstly, you can use the reticulate package, which basically allows you to, from within an R environment, address a Python kernel. And then with pyrunstring, for example, you can basically just run any Python code you want. So you can import your FastAI library, and then you can define a Pythonic object to host the model and some data, and then use FastAI's way of training that model. Now, alternatively, you can actually do something more native to R. So basically, you can import the library to an R object and basically have all the elements that you're dealing with as R objects. So in this second setup in the middle of the slide, you actually, the learner object is actually an R object. And all the parameters you're using, all the data is actually hosted within R. So this is particularly good if you're actually willing to mix the two. So if you want to process your data in R, maybe analyze the results in R, but just have the modeling, so just the fitting in Python, because for some reason you want to use the FastAI library, which I, by the way, advocate. I think it's really great. But there is also another way. So both of those approaches require you to know FastAI. Or to know Python well enough to be able to run this modeling. But you can actually do even more, or go even simpler. So what you can do is, in your R environment, you can import whatever Python model you have to your R objects, and then you can use them to run inference on your data represented in R. So this scenario is particularly useful if, for example, you want to build an R app, let's say a Shiny app, in which you want to host a model that was trained by someone else, for example, our model, and the model comes from FastAI. You can still import that model to your R environment and make use of it in your application. So this shows us that even staying on your warm R sofa, you can still make use of the latest developments on the Pythonic side of machine learning and computer vision in particular. So with that said, I hope to have argued that you have the skills to help serve the world. So please use them the best you can. Thank you very much. That was all I have prepared for today.
Yeah, thanks, Jędrzej. If you can stop sharing the screen, we can proceed with Damian.
Okay. Okay. Welcome, everybody. I'm really happy that I can give this talk today. I will be talking about scaling Shiny in AWS. So I will give you some advices how you can benefit from using AWS when you want to host your Shiny applications. Quick introduction about me. My name is Damian Budelewski. I work as an infrastructure engineer at Epsilon. I have a background in Linux, administration and cloud. especially AWS. So agenda for today's presentation is that I want to give you a introduction on how you can scale Shiny applications. Then I will talk a little bit more about AWS services that can help you with that. And at the end, I will show you the example costs of such architecture. It often, when a developer creates Shiny application, he isn't aware of the possibilities and how quickly it can become a very successful app, and how fast people that starts using it, they share with other friends, and the app can be really overwhelmed. So, and when they host the application on single machine, it probably won't handle such traffic. In this talk, I will talk about also Shiny Server open source, because I think it's the most used platform for new Shiny developers. But when we talk about scaling, we have to understand one limitation from this on this platform, and it is and this limitation is about serving the application on a single process. So you can see here, when one person starts his computation on your application, then the other one will have to wait until it's done. Okay, so what you should think about when you create your application in Shiny, and you want to make this app scalable? So you should take care of leveraging your front end, so the computation can be done in the browser using JavaScript that do not change the data. The second option is extracting computations. So if you know that your application will have maybe some heavy computation that you so if you know this, you can extract them to remote hosts and set the architecture so it's prepared for such traffic, like high traffic in different times. So this I will talk mostly about setting such architecture on AWS, and a little bit about extracting computations. Okay, so what options do you have on AWS to like pricing options for virtual machines on AWS? The first one is the most basic, is on demand. You pay for compute capacity by the second. And this is mostly you want to use this instance when you want to define your needs. You want to prepare the table, how much resources your app will use, so you know the expected resource needed you will need. The second one is reserved instances. It's just the option that you can pay upfront for your machine in 1 year or 3-year term, and you will just save the money because you pay upfront. Saving plans, they are mostly the same as reserved instances, but they allow you to be more flexible when it comes to changing your instance types or regions. And spot instances, it's an unused EC2 instance capacity. And this is especially for fault-tolerant stateless workloads, like, for example, backend APIs or web servers. Okay, so let's start describing it a little bit more. When you want to save money by buying reserved instances, you're not buying a physical instance. you are buying a discount for on-demand instance. So it's like when you have your on-demand instance up and running on AWS, and you buy a reserved instance, then it will have a discount and you will not pay for it anymore. With spot instances, it's different. You have like this type of instances let you take advantage of unused EC2 capacity in AWS Cloud. And you can save up to 90% compared to on-demand price. But it comes with the logic behind the spot instances is that when AWS isn't using the capacity, it can sell it to you with a big discount. But when EC2 reclaims the capacity back, because more users starts to creating on-demand instances, you will have to return the capacity, and thus it means that you will have to, like, EC2 will hibernate, stop or terminate your instance depending on the interruption behavior you set up while setting the machine. So this is just for the applications or services that are fault tolerant and can be interrupted. And I saw the question in the previous, like Martin was talking about EC2, and someone asked if they can create an instance that can last for few hours only. So you can do it with EC2 spot instances. You create a request for spot instance for a duration of time. So you can say, right now you can say that I want to have this instance up and running for 6 hours. And after this period, the EC2 will be terminated. And you have also a very cool tool. It's called Spot Instance Advisor. Because you might know that in the AWS, you have very different instance types and instance like family, instance families. So you have maybe general optimized or memory optimized. And in spot instances, they have different savings because of the way the capacity is used in EC2. Maybe when the instance is very little used in the whole AWS, you will get more savings from picking this instance. Okay, so we talked about pricing options, and now we can go to scaling. So the basic concept of scaling is that you can scale vertically. So you can add resources to your instance by adding more, for example, RAM or CPU. And you also can scale horizontally. And this means that you can create more and more machines. And in this image, you can see that the size of this of this person is the same. And in AWS, you don't have to spin up the same machines in the group. You can use different types of machines, and this will help you. Like, you don't have to go using the same instance type. You can have two bigger instances, maybe one few little ones, and so on. So in AWS, you can do it by using auto-scaling groups, and it will automatically adjust capacity to maintain steady, predictable performance at the lowest possible cost. And this is the use case where you have your application up and running, and you want to be able to handle the traffic that is not, how you can say, it's not the same all the time. because maybe in different times or different days, the application is not used as much as in the other ones. So instead of buying 4 big instances, you can set auto-scaling group that will manage your instances by scaling out and in. So you scale out when you want to have more and more instances and the high traffic peaks, and you will scale in by terminating the instances when you don't want to overpay for your compute resources. And you have EC2 fleets. So this is the case when you have when you want to save money by buying these spot instances, and you can, like, your application can be run in different on different instance types. So it doesn't have to be T3 medium. You can have multiple different instance types, but you want to have the cheapest one that are available. So this helps you with that. And it can also ensure that you always have the instance capacity, because the spot instances can be interrupted. And you can create a request for on-demand instance, and this will allow you to have this capacity always. A very cool feature from AWS. They introduced this few days ago. It's called instance rebalance recommendation. So it's a signal that notifies you when a spot instance is at elevated risk of interruption. And this means that when you have a spot instance, it will always get a notification when AWS wants the capacity back with the 2 minutes like before. And this signal can arrive even sooner than that. And you can set your Amazon auto-scaling group to use this signal to proactively replace spot instances in the group that have received this signal, so they can rebalance your workload to new spot instances that are not at elevated risk of interruption. So the EC2 auto-scaling group will take care of changing your instance types to those that are available right now. And I talked about it because we have Shiny that is stateful. We have maybe Plumber API that it doesn't have to be stateful. It can be run in such instances. So what we talked, like we divided the two options of scaling and saving money by extracting your computations and setting the scaling architecture. So with the spot instances, you can host your Plumber APIs there, and this can be interrupted and you will save money. And with the EC2 instances, by buying reserved instances, paying upfront, you will host Shiny applications there. And so with the cost, so resource usage for your Shiny application can vary a lot. You can have an application that will use 50 megabytes of RAM or even 1 gigabyte of RAM. And it really depends on how much data you will load to your application and from the platform where you host it. So it's very hard to predict those numbers, but you can see this is a example how much you will pay on AWS by using just on-demand instances, so with no cost optimization at all, depending on the concurrent users in this app. And if you decide to cut down your costs by using spot instances or reserved instances, you will save a lot more. Like you will save save maybe a half or 70%. And you can see this table is divided to two options because, like I said, spot instances are not the best option when it comes to production environment. So it can be, but with the workloads that are stateless, like Plumber API. And maybe development environment, when you don't really care if your instance is terminated, you can handle it, you can accept it, and you will save money by using spot instances. But when it comes to production and you only have one instance, it's better to just pay upfront for reserved instance. And you can save, for example, 50% comparing to on-demand price. And when we were talking about auto-scaling and spot fleets, you can just add here the prices, like when you have auto-scaling group and you have on-demand price for 2 instances, you can just buy 1 reserved instances because you know that your application will always have to have the capacity, at least one instance, and the second one can be just on demand, turning on and off during the day. And when it comes to Plumber API, and you have auto-scaling group with the spot fleet option, you can use on demand and spot instances depending on the depending on the capacity you need and costs you want to save. Okay, so summary, like I said, the spot instances are for stateless and reserved for applications like Shine. And what I want you to remember from this call is that you have a lot of options to save money on AWS, to use different types of machines, to use different types of scaling and different types of pricing options. So just have that in mind and explore this so you can optimize your costs. Okay. Very thank you. This is the last slide from the from Epsilon that we have offers, job offers, and if you want to take a look at it more deeply, just open Epsilon.com careers. Okay.
Thank you so much, Damian, for the great presentation, and Dr. AJ. Well, so there have been a few questions on the chat box, so we'll start with questions regarding the first presentation. So I hope I'm clear enough. I got rid of my microphone or something. Yeah, so it was a bit noisy. Okay, so Dr. AJ, there are a couple of questions for you here. So first, there's a question. Someone wants to know whether the computer vision analysis will be possible to be applied in different parts of the world. So how will you respond to that?
Yes, certainly. There have been such efforts. We have focused mostly when it comes to analysis of images of animals. We have looked at Africa. However, I know of studies done in different parts of the world. But you have to understand that it's not only that there are obviously different species in different areas, in different ecosystems, but also the conditions are very different. So a typical problem that you have in the forest setup, so the one we worked on in Gabon, is that you basically have a lot of foreground. So everything on the image is the foreground. There are a lot of trees, a lot of leaves, everything is jumping right into view. And somewhere there you need to find the animal. But to give you a contrast with, for example, the Arctic setup, where there are systems trying to identify polar bears, the problem there is that you have an empty landscape, and the polar bears can be anywhere on the image. So they can be right in front of the camera, or they can be tiny a few pixels somewhere near the horizon. So then there are very different problems that you need to deal with. Actually, an example of that was a competition that we participated in, which was also held based on African data, but this was data coming from the Serengeti National Park, which is located in Eastern Africa. And it's actually not, it's mainly savannas. So it's basically a bit closer to the Arctic setup. So you basically just have an image of, half of the image is grass, half of the image is sky, and then there are some animals somewhere there. So you typically see a few species in an image because there are some zebras in the front and some gnus or hartebeest in the back, and you need to identify which is which.
Okay, thank you. Maybe, Marcin, do you want Damian to take one question before Dr. AJ takes another one?
I think let's have all the questions to Jędrzej, and then I will pick on and follow with Damian. Okay, so Dr. AJ, the second question from Makama. So for the models, so does it mean that they can import the model in our environment without changing it to any other format and still use it?
Yeah, so I think I know where the question comes from. So it is a typical problem in let's say using machine learning models, that once you have trained them within one setup and you want to make use of them, so run inference from a different, slightly different setup or in different libraries even, or different languages, you need to translate, and this is a pain. I've been through that, so I know it's a pain. In the way that I've shown you, you actually don't have to do that because you're still using FastAI to load a model that was trained in FastAI. I've tested this on FastAI, but I can imagine you can also do that for TensorFlow models. So you can try to host TensorFlow or address a kernel running TensorFlow from within R using Reticulate, and then load the TensorFlow model with the same version of TensorFlow. So indeed, in those examples that are present in the repo that I've shown you, so the FastAI-in-R repo from Epsilon, you will actually see an example for yourself that there is no translation whatsoever.
Okay. Well, so thank you. So the third question is it possible to have similar analysis done using the photos from the drone?
Yeah, thank you for that question. There was another one with satellite images, I believe, as well. So yes and no. In principle, aerial images could assist our analysis, and I know that there was even a competition in which I think it was the iWildcam edition, one of the recent ones, in which there were images of like aerial images of the region from which the camera trap images came from, which were given for the participants to get insights from them. I'm not aware of how that can be done effectively. And while in principle you can think that you can get some maybe statistics about the color in those images, there are many problems there. And in our particular case, there's just no way this is going to help because of the fact that we are in a dense forest. So those animals simply won't be seen. You will see the crowns of the trees. So that's just not going to help in this particular case. In others, maybe, but I'm not aware of any successful attempt at this.
Okay, great. So Ian wants to know what's the size of the image training set?
Thank you. That's a very good question. So I've mentioned that the data set that we got from the experts was over 1.5 million images. But because of a typical problem in such data sets, namely class imbalance, and also because of the fact that a large portion of those images were actually empty images, which you can also think of as sort of an imbalance problem, we have actually trained the models on a subset of roughly 300,000 images.
Oh, okay, that's a lot of images. Yeah, so then there's I think a similar question with the one for photos from the drone. So Dasala wants to know whether it's possible to use satellite data in this computer vision project.
Yeah, so as I said before, in principle, yes, but I'm not aware of a successful attempt at this. Because these days, well, okay, it depends on the setup, but the satellite images can be actually of very good quality, of course. Can have up to 30 centimeter resolution. And then, I mean, that's the legal boundary. Of course, technically you can have even better, but that's, I think, only military grade satellites. But I'm not aware of a system which could which would use that. Although I can imagine that in an Arctic setup, that's the best way to go.
Okay. Okay, thank you. So Makama wants to know, so when fitting the model, so when doing the modeling part, so is it possible to use the model weights and not the whole model architecture, just in the just as the case of transfer learning?
Yeah, so this again touches on the problem of so this typically happens when you have your training setup or someone's training setup, and then you're trying to use the model in different setup. So the question is, how do you translate? How do you get transfer the knowledge from one setup to another one? And one of the ideas would be, let's take the raw numbers, so the weights, and just put them on the skeleton defined in a different setup. Well, the challenge here is to make sure that the skeleton is actually the same. So a typical example is that you take, let's say you take a model trained on a ResNet backbone, so like a residual network of a given depth implemented in one library, let's say PyTorch. You take its weights, and then you want to use those weights for the same architecture or seemingly the same architecture, but just implemented in TensorFlow. Well, what typically happens is it turns out that it's not exactly the same, the implementation. There are some implementation details, for example, of different types of neurons that make the model, even if it runs, it actually makes it much worse, because some neurons work slightly differently with those weights. So you have to be very careful when doing that, and I would try to avoid it at all costs.
Okay, great. So I hope Makama, you have been answered there. So the final question for you, Dr. AJ, is from Brian Wangi. So Brian Wangi wants to know whether such good projects like this computer vision, can it be open source so that people can learn, implement, and tweak a little bit of the code and so forth?
Yeah. So I think not only they can, but they should be open sourced, and in many cases they are. So our projects were or are open source. As I've mentioned during the talk, I've mentioned the repository for the Embaza app, which is, I believe, Epsilon/wildlife-explorer. But also the training code, which I've used for training the model, is also open source. And you can find it on GitHub at Epsilon/Gabon_wildlife_training, I believe. Let me have a quick check, but I think that's the repo. And basically, yes, Gabon wildlife training. So there is one caveat though. Even though the code itself for the training and some discussion of the parameter settings, some exploration and notes of the training sessions is available there, the data itself is not. And the reason there is that for this study, we have used data collected in multiple projects from multiple scientists. They all have their own funding, and they all have their own setup in which they've collected the data. And therefore, there are multiple rules related to data sharing. So we haven't shared that data yet. Good news is that I expect large parts of the data to be available because we are now in the process of publishing the paper that I've mentioned. And for that, we hope to publish large parts of the data after, for example, anonymizing the location in which they were taken. Because you can imagine this is very valuable data for the poachers, for example, to know that a certain elusive species was visible or where it can be seen.
Thank you, Dr. AJ. So those are the only questions that were available to you. So, and thank you very much for the nice presentation.
Thank you for
Over
the
to you,
question.
Marcin.
Okay, I will pick it from there. Damian, we've got a couple of questions regarding your presentation. It looks like you're an expert in managing AWS costs and running Shiny applications. So there are a lot of tough questions for you. Let's start with this one. Maybe you have an experience. What is the best strategy of scaling Shiny apps that get their data real time from APIs, from web-based databases, such as Redcap or MySQL? Do you have experience with that?
Okay, so it really depends on where the problem is. Like I don't see here like any, because it's like the normal situation where you have Shiny app that is connected to the database or something like that. And this is just a normal situation where you can use like the auto scaling group and just make sure that you have all health checks that say when the instance is up and running, that the Shiny can connect to the database, make some queries, and the app is ready. And when all these health checks are done, then you can attach this new instance to load balancer. I don't know if I answer it correctly, but I hope so.
Christopher, would you like to elaborate on the question? Maybe you have more ideas.
Okay, so actually, what I was thinking of is, so you have your live database somewhere on a web-based server or a setup relational database management system, whereby your Shiny application is getting data from. So you really don't have a static data somewhere. So this data continues growing. So then you manage to leverage the use of APIs to basically pull it as it gets populated. So at some point there will be like a bottleneck as it grows, as the database grow larger, and probably the turnaround time between communication between your Shiny application and the database might delay your output on the applications. I was wondering what is the best strategy to actually be able to avoid such scenarios from catching up with you when you are trying to scale up your apps.
So we are talking about scaling at the same time the database with the Shiny application. So in AWS also provides it. You can have clusters or a cluster of databases that can scale the same.
Okay, thank you. Thank you.
Damian, looks like you are experienced. So happy to have another question for you. Is there any threat when hosting a Shiny application on AWS? Is there any way people can get your data from a Shiny app or can access your server through the Shiny server and can they do any damage?
Okay, so I think it's up to you, like how much you will prepare your instance to such situations. Will you use all the best practices available to make your VM secure as possible? And we are talking about platforms. So for example, platform like RStudio Connect can be very secure. You have authentication there. You can define who can access it. Maybe you can have authorization with Google and with the Gmail and so on. So this will allow you to block any unwanted users on the platform stage. But when it comes to virtual machines, you also want to have, for example, blocked ports that you are not using. You want to have store your passwords like keys in the proper password manager and so on. So if you are using all of these best practices, the risk should be very, very low.
Alrighty. Good to know that this can be a very secured solution. All right, let's talk about some sizes. Would you mind sharing what was the biggest project that you were involved in? How many instances involve your biggest Shiny application? How many users it had per day, or even at the same time?
Okay, so at Epsilon we had like the very big project where on one application was used by 700 users, concurrent users, but I don't have the statistics or of how many instances were running. From my experience, I have the projects where I have 5 very big instances that handled the traffic, and it costs around like a few $100 per month.
Few $100 per month.
Yeah, because we had like very big instances there. But this is the way with the time it was optimized out.
Got it. And how many applications do you have running at the same time?
Like the applications, I don't understand. Like for example,
so you needed
Mhm.
you needed 5 instances to run one app or run one Shiny server with multiple applications.
We had one applications there, but it was so RAM consuming because one user can allowed like few gigabytes of RAM. So the app was really resource consuming because of that.
Okay. And what was the biggest invoice you had to pay for EC2?
Like I said, it's like few $100, I think.
That's much. Alrighty. A question from Hyun. What is the best way to handle long-running database queries in a Shiny dashboard?
So I think also it's not the Shiny case. I think it's more like database configuration. You can have multiple ways of improving the time of the queries, like indexes, or even you can change your database to, for example, Elasticsearch, which is very like fast. And you should be like focused on this side, on the database, and how do you make the queries, and not the Shiny.
Okay. And I think those are all questions from the chat as for now. Damian, could I ask you to show your last slide so we can see the positions that you have at Epsilon? And maybe I will have a few questions regarding those. So my first one is, and feel Jędrzej to step in. Are there any requirements for the location? Is it worldwide open recruiting, or is it limited to some time zones? How does it look?
I'm not aware of any limitations. We have actually recently hired people from South America. So yeah, we don't have currently anyone working with us from, let's say, Asian time zones, as far as I'm aware. But we did have, so we did work with a person who stayed there. So it's also possible. Yeah, so I highly recommend, and definitely nowadays we work fully remotely. So whether you're located in the same city or a different country, it doesn't really matter that much.
Okay, so that's worldwide open.
Yep.
Good. And if I am just an R user, can't use Python, and have like limited knowledge about AWS, would the R Shiny developer position be a fit for me, or do I need any other stack to be aware of?
Well, you definitely should be aware of as much as possible. That's of course a pro. But we have multiple roles and multiple paths within the company. So I would say that as long as you have skills that can impress us, and you're willing to learn others, you definitely should apply.
And could you tell something more about the full stack or the senior infrastructure? Is it more for the general purpose programmers or for our users? What is the target audience for those two positions?
So Damian, would you like to describe that?
I can say about infrastructure engineer, of course. So I think mostly you have to understand the automation tools, how to set up the infrastructure in clouds, and the tools like Terraform or Ansible. It's also good to understand programming in R or Python. And because we are developing Shiny, it's necessary for you to understand how the platforms for Shiny works, like RStudio Connect and Shiny Server and so on, and cloud services, because we mostly use cloud. Like we only use cloud, we don't use any internal infrastructure like hosted in our offices. So you got to know this stuff.
All right. And how does the typical hiring process look like? Do you look at LinkedIn profile? Is CV needed? Is there any homework assignment?
Yes, we of course, like I think all the IT companies these days ask you or ask candidates for completion of homework assignments. However, it's good to discuss with your hiring manager, so to speak, or the person you're in contact with, exactly what are the ramifications of that homework. So how much time you can spend, how much time you're willing to spend on that homework. And then the process typically consists of first you need to apply with of course with your documents. Definitely a LinkedIn profile is a must. I would say also some sort of repository or portfolio, depending on the position you're applying for, is definitely a way to impress us from the early stages of the process. Then typically you would have 2 to 3, I believe, interviews, depending a bit on the position and the situation. Somewhere in between is the homework that is then discussed, and we are so we give a lot of we put a lot of stress on feedback. So it's important for us to get feedback from you about the process, about well, let's say your experience, but also therefore we give you feedback. So yeah, so of course it's important that that we all learn from that process.
Okay, there's one question on the chat actually regarding the hiring process. Do you hire an uneducated enthusiasts that are willing to learn but are not experts yet?
Yeah, I would say so. Of course, it depends a bit on the position, but we have examples of people who are self-educated, so who are, or sometimes they are educated, but in a very different field, and then they just are very interested and have invested their own time into jumping into a new subject. And then if they're good and well and willing to learn, then that's a perfect setup. So I myself have been in that position some time ago, because my background is in theoretical physics, so it was very theoretical, so it's very far from dealing with any sort of data. And then I decided to jump into machine learning, and well, so yeah, I definitely see a path there.
Okay. Thanks, Jędrzej. Thanks, Damian. I think we can call it a day. Thank you for preparing the presentations, and for the audience for all the questions. Thank you, Christopher, for joining and being a host. And guys on the audience, if you are interested in joining Epsilon, there are links in the description of the video that you can always refer to when looking for those job positions. And yeah, thanks for joining, and see you next week the very same time.
Thank you for the opportunity.
Thank you, guys.
Okay, thank you. Bye. Bye, guys.
Bye.